Good morning, all of you. In today's class, in the chapter Electrostatics and Gauss law, the topic we are going to discuss is about the earthing of shells. Like if there are 2-3 shells are there, then what is the potential of individual shell and what is the electric field everywhere? Then after that, the potential difference between the shells. Then if I earth one of the shell, or if I earth two shells, if I connect the two shells by a wire, so what has to be done? So again, the what all know till now we discussed the basics of the Gauss law that we are going to see now. The application part is what you're going to see now. Okay, let me take you to the screen. Okay, I do have two concentric shells A and B. There are two concentric shells A and B are given charges Q. What are these? These are the thin conducting shells. I think I forgot this. Thin conducting shell, conducting concentric shells A and B are given charges Q1 and Q2. What will be the potential electric field everywhere in the region, and also the potentials of individual shells and also the potential difference. Everything has to be determined. Now, do we know potential due to shell? What we discussed for conducting spheres, same thing. Can you recollect conducting sphere? What will be the potential everywhere inside the conducting sphere, charged conducting sphere? Will be that on the surface. So same thing happens with the shell also. So what all we discussed for a conducting sphere, the potential electric field, the same thing applicable for the shell also. Hope everyone is able to recollect. If you forgotten, go for the notes, turn the pages, there you can see clearly. Fine. Okay, now it is given like this. So how to calculate that potential? So to calculate potential, I'll take help of superposition principle. To calculate the field, I'll take help of the Gauss law. These are the few things which I'll be taking care here. Let me hide it. Yeah. Yeah. Now we'll proceed like this. So first, actually, the shells are given charges. You see that one. This is given Q1 and this is Q2. This charge Q1, what it do? It will induce charge. So overall, the final the situations that will occur is here charge Q1. It will induce a charge minus Q1. What is the charge on outer surface of shell? Q2, no? The total charge will become Q1 plus Q2. This will be the charges on each surface. Okay, the first problem, no? Okay, we'll start like this. What is the surface charge density here? I'll call sigma 1. What is the surface charge density here? I'll call sigma 2. Let this be sigma 3. Can we calculate sigma 1? Sigma 1 should be equal to Q1 by 4 pi A square. What is the surface charge density of the outer shell? Q1 plus Q2 by 4 pi B square. What is the surface charge density of inner surface of the shell B? Sigma 3 equal to minus Q1 by 4 pi B square. Agreed? This one? So this will be the charges. Now he's asking to get the potential. So now whether you consider this induced charge or not, you're going to get same answer. I'm going to change there's a one part. Okay, now we'll take the, so every time you need not to go for this as they're thin shells, no? You need not to bother about this induced charge. Even then you'll get the same answer. Okay, looking at this diagram, we'll find. First, we'll choose the point. Let me choose the point P1. Now, what shall I do now? So here, this is the R1, or shall I write R? So where is the point? This one. So there the electric field I want. So what shall I do? I will draw a Gaussian surface. Then where this charge plus Q1 will be on the surface of the shell A, plus Q2 charge will be on surface of shell. In fact, the charge will be like this. Here plus Q1, here minus Q1. And what about here? Q1 plus Q2. They'll be distributed uniformly. Yesterday we have seen all that one. Then when I draw a Gaussian surface, where do this whole charge will appear? As it is the charge is distributed symmetrically with respect to center of Gaussian surface. So where the whole charge? Okay, I think there's the first problem. Let me draw the Gaussian surface. What is this? This is a Gaussian surface. And look at that. These are symmetric charges. The charge is distributed symmetrically. Then what happened is the whole charge plus Q1 on shell A will appear at center. Even this also appear at center. No, sir. Now I look at this and draw it. Okay, there also no problem. Plus Q1 minus Q1, Q1 plus Q2. How much of net charge at center will be Q1 plus Q2? So now we know what is the electric field strength. EP1. This should be equal to K Q1 plus Q2 R square, where R should be greater than B. The point lies. Similarly, what is the potential? K Q1 plus Q2 by R. Okay, I agree this. I'll come to the later. Okay, let me choose the point now somewhere inside. Huh? Let the point be the point P2. What about the electric field and potential? So let me write this as distance. Already A is there, no? I'll write R. Let me write R only, no problem. Where what is the condition for R? R should be less than B and greater than A. What about the field strength there? First EP2. What I'm going to do is I'm going to draw I don't have a space now. I'm trying to accommodate everything here. I'm going to draw a Gaussian surface here. If I draw a Gaussian surface, then what is the net charge enclosed? Will be only Q1. Okay, I think, yeah. I'll slide down, no problem. Yeah, we'll take this one. There's a first diagram for first problem. No, I'll try to give detailed explanation. This is a Gaussian surface. Tell me, like, what is the dotted line? Understood? It's a Gaussian surface here. What is the net charge enclosed by Gaussian surface? Only the charge Q1, and that too, it's the charge is distributed symmetrically with respect to Gaussian surface. So where do all this charge plus Q1 will appear to be at center? Then similar to like a point charge, what is the field strength will be? KQ1 by R square. Now you can ask very best question here. Sir, this charge is there. Will it produce field anything? Yes, it will produce. Even the symmetric charge will also produce. Due to symmetry, distribution of charge Q2 on shell B, the net field at point P2 due to Q2 will be 0. Don't say it will not produce field. The net field contributed by the charge Q2 on shell B at P2 will be 0. You have to write this. You can't listen. Huh? If you just listen, it's not like some TV serial. You can't just listen. Some things which I'm stressing are very fundamental. Immediately you should scribble it in your notebook. So what is the point P2? What is the condition? The charges on all surfaces will contribute field at point P2. Then the net field at point P2 is but only due to Q1. Why not due to Q2? The resultant means even if you take this particular sector, it will contribute field. This other sector will contribute to equal and opposite field. Net field will be in fact 0. The net field, the net electric field at point P2 due to charge Q2 on shell B will be 0. There's a condition. Then only Q1 is what contribute. I'm writing. So what is the condition for this R? R should be less than B. You're supposed to think, analyze, no, just only mere listening, not possible. No? Okay, there's about the electric field. What about the potential? Potential is due to superposition of surface, due to superposition of charge on all surfaces. When it comes electric field, only charge enclosed by Gaussian surface will contribute the net field at point P2 on the Gaussian surface. When it comes potential, due to superposition of charge on all surfaces. So how to write expression for potential? Potential is given by, first we'll go for superposition. Assume that only charge on shell 1 is present, then at what distance it is. The point P2 lies outside. Go for conducting sphere. What is the potential outside a conducting sphere? KQ by R. It's similar to this one. KQ1 by R. Then if shell, inner shell is not there, only outer shell is there, what is the potential? Go for conducting sphere. What is the potential inside the conducting sphere? That on the surface. So same thing for shell. So now assume that inner shell not there, only outer shell is there. Then what is the potential on outer shell? KQ2 by B. And that should be the potential everywhere inside. So the formula will become KQ2 by B. I think this will be very important. When it comes field, we took Gauss law. Net charge enclosed by the Gaussian surface will contribute field there. When it comes potential, what we did? We took superposition. The charge on all surfaces will contribute here. Q1 will contribute potential, Q2 also will contribute. Point P2 lies outside this shell. So therefore what will happen? KQ1 by R. Then you assume that this inner shell not there. Then where this point P2 lies inside the shell, and what is the potential inside the shell? That on the surface. Anybody having doubt, please clarify. Strictly there's a condition for R. R should be less than B and greater than A. Okay, so this is about the potentials. Okay, now I want potential somewhere inside. So let's get into this one. No. Okay, this is not needed now. Where is the point? No, the point will go inside the shell A. At point P3. Shall I write 0? Strictly what is R? R is less than E. What about potential at point P3? We should do why 0? Because where you are drawn Gaussian surface inside the material A, like inside the shell A. So what is the net charge enclosed by Gaussian surface? 0. So electric field is 0. Then potential at this point, we should go for superposition. Then first only due to shell 1, shell A. Now where the point P3 lies inside the shell A, what is the potential inside the shell A? That on the surface, similar to conducting sphere again. So therefore the potential should be KQ1 by E. Then afterwards, only due to shell B. Assume that shell 1, shell A is not there. So where the point P3 will lie inside the shell B. Then what is the potential inside the shell? That on the surface. So KQ2 by B. Shell or conducting sphere, both are same. You can write in your notebook. Electric field and potential, what all we determine for conducting solid conducting sphere is similar to that of the shell. Thin conducting shell. Now, what will be present here? Air, vacuum. Only the iron is present here. This pink color is what? Iron. Concentric shell, able to assume all of you, football, volleyball, made up of some iron, thin iron sheet. We are discussing of that kind here. So if you are getting confusion, no, write it. This is iron. This is a copper. No, okay, nothing wrong. Huh? You can take help of such things. I'll write it here. Okay, conducting also, it may not flash you much. Okay, this is about the field potential at various points. So now I want potential of individual shells. I need fresh one more page. Just it's a procedure method. Already we have done a little bit in gravitation, but here a little bit more cases will come. Okay, no, I want the potential of each shell. What shall I do? Shall we take help of this condition only here? Coming. Yeah. I'll remove all these things. So what we want exactly, I want potential of shell A and B. What is the method? Again, once again, you can use that formula. So once again, we'll use the same thing. When you're calculating potentials, what we should do? We should just take the superposition. All of you do follow. Just look at the screen. It will be a potential at point A. Now, first, what happens? I'll assume that only shell A is present. Assume that shell B is not there. This Q2 shell B is not there. Then what is the potential at point A? Given by, it lies on the surface. So KQ1 by A. Then assume that shell A is not there. Only shell B is there. Charge Q2 and shell B is there. Then where is the point? No, the point lies on here inside the shell B. What is the potential here? Potential on the surface of shell B. K Q2B. Trying to follow. Potential comes, superposition your top right. Similarly, potential at B. Potential at B. Again, first assume that only shell A is present. Here at this particular point, only due to shell A. Now, where the point lies? The point lies outside the shell A. So then this will become like this. Just wait. Can I'll just some. Look at this one. No, potential at B only due to shell A. So where the point lies outside, and at what distance from the center B? Plus. No, where is the point I'm finding out potential here? So I assume that shell A is not there, only shell B. Where is the point? Point lies on the surface of shell B. So what is the potential on the surface of shell B? KQ2B. These are the potentials of shell A. What is this? Potential of, this is potential of shell B. Just you have to practice it. And now let me find out potential difference. VAB, VA minus VB, let me calculate. So KQ1 by A. KQ1, KQ2B get cancelled. So we'll get KQ1A minus KQ1B. Look at now. So what will happen to the charge on this shell will not determine potential difference. If I add or if I remove some charge on shell B, what will happen to the potential difference? Independent. So what is the conclusion? VAB is, or potential difference, let me write sentence, potential difference between shells is independent of charge Q2 on outer shell B. Whether you add some charge. Now for this, if I add some charge, potential of A and B will change, but potential difference will not change because independent of Q2. Now I'll remove some charge on shell B. Then also the potential difference will remain same. Potential difference between shells is independent of charge Q2 on outer shell B. Getting the idea? And these are some very fundamental things. Now, so like just very simple. Again, the thin iron shell. So first I'll add a charge. Where do the charge? It'll go and reside on the surface. I'll add a charge Q1. So shall we put the charge where you have to show, in fact, like this? The charge will reside only on the surface, will not go inside. Means, sir, can it happen like this? The charge, there's iron shell, I need to write every time. So charge will go and reside on inner surface. Which one is correct? Thin iron shell, charge Q is given. Now, where do the charge will reside? Will it reside on inner surface or outer surface? It should reside on outer surface, not on inner surface. This is a wrong thing. Fine. Huh? This will be. I'll agreed. But you can really trouble teacher like this, sir. Okay, are you sure charge will not reside? What I'm showing here, charge on inner surface of shell also, no? These are the things where student was supposed to analyze things. But sir, you said charge. Here concentric shells are there. Okay, there'll be like electrostatic induction will occur. And now you have to ask one more question. So why minus Q1? Why not minus Q1 by 2? Anybody? Why not minus Q1 by 2? Why not minus 2 Q1 here? Plus 2 Q1. Why minus Q1 only? So what is this? There's a conductor. No, you are going to draw a Gaussian surface in the material of shell B. Then what is the net field inside the conductor? Should be 0. I am exploring this one. These are very fundamental things where student was supposed to analyze. Okay, that one. So this is wrong. Okay, now again, let me go back to the same idea. There are two shells are there. They are given charges Q1, Q2, the same thing. Why the charge minus Q1 plus Q1? Actually, what happened? This is the shell A. The shell B, what happened? Little bit thick, I'll make it. To make you understand. I know still more thick is needed. It's not thick shell, both are thin shell only to make you understand. Then what we do is like we'll draw a Gaussian surface. Both are thin shells. Huh? Both are thin shell to make you understand. So here is what we have point P. Tell me like what should be the what was the charge? The what all charge given plus Q1 will be here. We know that. What about minus Q1? Minus Q1 will come on inner surface. Agreed? Minus Q1 will be charge on inner surface. Sir, why only minus Q1? That was the primary question. Why not minus 2 Q1? What should be the net field at point P? Net field at point P must be 0. Am I right? Net flux should be 0. Net flux should be 0. Net charge enclosed should be 0. So naturally, so how much you get here? If Q1 is there, minus Q1 must be there. Agreed, all of you? Why we should think in this? Everywhere the gauss will come into picture. So here, though it's a thin shell, I just to make you to show that gauss, like a Gaussian surface, I am making thick. It's in fact a thin shell only. There's a shell A and shell B. Agreed, all of you? So why it should be minus Q1 on inner surface of shell B? There's a reason. And now you can ask question like, you didn't consider such minus Q1 and you solved it. Whether you consider the induced charge on inner shell or not, the final answer will be same. Check it. So minus Q1 plus Q1, you write it. Solve it, you'll end up with same answer. When thin shell comes, you need not to bother this induced charge on inner surface. Thick shell comes, you should consider. Agree, there's a lot of confusion. Some books, they consider this and solve it. Some books, like what I did, I didn't bother this minus Q1 and plus Q1 on the shell B. I will get the same answer. If a thin shell comes, you need not to bother about the induced charge. Directly proceed. But if they ask you something surface charge density, then you must work out. But when calculation of potential and electric field, you need to bother this minus Q1 plus Q1. Because what is the net charge of shell B? Still Q2 only. I'll put, I think there's a very first fundamental problem. Have a clarity. The same thing we are going to repeat. Nothing new will be there. Any doubt? If you have, you can clarify it. Okay, all of you, I think minus Q1, why only minus Q1 from Gauss login? For thin shells, whether you consider the induced charges or not, you'll get the same answer. Okay, agree this? This will be the potential difference, there's the condition. Okay, let's similarly, we'll start with the three shells are there. It will become good practice for us. So we have, okay, I think I'll write radius R, 2R, 3R. Three concentric shells, three thin concentric conducting shells. Read this one. Meanwhile, I'll add that thin conducting. Okay, no, three thin conducting concentric shells A, B, and C are given charges Q, minus 2Q, 3Q. Find potential of individual shells VA, VB, VC, and work them exagent in moving a charge Q0 from shell C to shell A. Now, what shall we do? What about the charge? Induced charges we'll see once. This will help us a lot. What about the charge here? Plus Q. If you are supposed to show everywhere on the surface, that will take time. So I'm just indicating only plus. It is understood. This charge will be distributed uniformly on the surface of shell A. Then it should be minus Q. Am I right? Then what was the charge of the shell B? The shell B was given minus 2Q, no? Minus Q, the net charge should be conserved. So how much it should be equal to? Minus Q. Then this will induce charge plus Q, 2Q. Okay, this will be the charges on all surfaces. Able to understand? So I'll start with this one. Charge here plus Q. It will induce charge minus Q. Then on outer surface plus Q, minus 2Q plus Q. How much will be minus Q? It will induce charge. How much it is?
It will induce charge minus Q, na sir. Minus 2Q plus minus Q is minus 3Q, na sir.
listen, plus q, minus q will be there, no? Minus q plus q will be induced, no? Minus q plus q will be induced.
Okay, sir. Yes, sir.
Okay, fine. Look at this. Minus q plus q. Plus q minus 2q, how much will be minus q? Then again, resultant how much here is minus q. So it will induce plus q, minus q. So 3q.
Understood, sir.
Okay, ma? Yeah. So what is the net charge of a shell will remain constant due to electrostatic induction. They're getting the idea? What was the charge of shell B, shell C? 3q. Okay, now also you see 2q, 3q. What is the charge of shell B? Minus 2q, minus q, minus q. What is the charge of shell A? Plus q. A very important sign means I may ask you such things rather than asking some numerical. These are very fundamentals. Even an advanced will ask you what is there in this one, because the student must know first the basic things. No. Okay, you can, looking at this diagram, you can find out the field, or you're looking at this diagram, you can find out the field potential, anything that it be. Okay, let's calculate first potential of shell A. And this is for your reference. They may ask you. I'll push it to corner. Okay, now looking at this diagram. Okay, potential of shell A. No, when it comes potential, what we should do? Superposition principle. First, only shell A is there. What is the potential on the surface? KQ by R. Plus. Okay, then potential. Now potential at point A here. Where is the point? Point is here. Assume that only shell A is there. What is the potential? KQ by R. Then assume that only shell B is there, but point is here. You are here. I think I'll give some symbol. I'm here. Then first only shell A is there. Potential how much? KQ by R. Then assume that shell A and C are not there. Only shell B is there. Then where you are inside the shell B. So what should be the potential that on the surface? So K minus 2Q by 2R. Then you are here. Assume that shell A and B are not there. Only shell C is present. But since you are inside the shell C, you are inside the shell C. So what is the potential on the surface? That should be everywhere inside. So K 3Q by 3R. So it will become KQ by R. There's a potential of shell A. Similarly, we'll take the potential of shell B. Now where we are now? Okay, I'll remove this person. The person is here. For your convenient purpose, I'm showing that person. You are here. First, only shell A is present. Shell B and C are not there. Shell B and C are not there. Then in that case, so where you are at a distance 2R from this. So potential will be KQ by 2R.
Sir, in A, you said that we should not electric. Okay, it's electric field. We are calculating potential. Yes, sir.
Potential superposition.
Yes, sir. Yes, sir. Thank you, sir.
Yeah. No, I'm standing at point like on the surface of shell B. Then potential at what distance I am at a distance 2R. So what is the potential due to shell A? KQ by 2R. Then what is the potential of the shell B? I assume that shell A and C are not there. Only shell B is there. I am on the surface of that shell. So what should be the potential that on the surface? Then shell A and B are not there. I'm inside the shell C. So the potential should be K . These two will get cancelled, no? You could have chosen some minus Q, you would have got some different answers. Any charges you can pick up, doesn't matter. Even this radius R, 4R, 5R also you can pick up. Okay, I'll stand now here. First, only shell A is present. At what distance? I'm at distance 3R. So therefore, this will be KQ by 3r. At what distance I'm from shell A? At a distance 3r. So potential should be kq by 3r. Then only shell B is present. Then shall we write 3r minus 2r? No. If you stand here, where do this whole charge will appear? So why you are writing 3r? So again, the similar to like you're standing here, you are outside the shell A. Then for you, what will happen if you draw a Gaussian surface? This whole charge will appear at center, like a similar to point charge. It should not be. It should be 3r only. You should not take the difference of this. Wrong. This whole charge plus q will appear at center for this person. It's an assumption like this from Gauss law. Similarly, the whole charge minus 2q will appear at center O for this person. So this will be K. And the person is on the surface, so potential. Similarly, if you want to calculate electric field here, suppose if you want to calculate the electric field, the field at this point is only due to charge Q, charge on shell A. If you want to calculate electric field here, the field here is only due to these two charges. The field here due to all three. Okay, we got the potentials, you see.
This is minus 2kq by 3.
Oh, this is minus 2q. I didn't see. Then I think it will be okay. 2kq by 3r.
Yes.
No. Is asking now. Is something is again troubling us. Work done extravagant in moving a charge q naught from shell C to shell A. Some test charge it is. So it will not produce. So if I'll write. I think the test charge will not produce its own field. So let's not bother change in potential due to movement of this charge. No. Any formula? Work done by extravagant in moving a charge from where? From shell C to shell A should be equal to Q naught into VA minus VC. Can you remember this formula? So we know VA and VC, substitute there. Q naught. VA is how much? KQ by R. Okay, this much of work the extravagant should do to transfer a charge, test charge from shell C to shell A. Now some work done also will be asked. Okay, first for that you should know only the potentials of individual shell. So what we have calculated, potential of shell B it is. Okay, now we started with 2 shells. Now it is about 3 shells like this, even 4 shells, let them give. Okay, we can manage. Thick shell, later tomorrow we'll focus on thick shell. You'll get confused, thick shell. Sorry, if I do for this also, will I get same answer as you'll get same answer? What is the net charge of shell B? Minus 2q, see, 3q. No need. But if I ask you surface charge density, you should think in this way. I'll scroll down. Next one, earthing of shells. So what is the primary concept of earthing of shells? What is the idea of that one? What is the potential of the earth? Potential of the earth, we consider it to be 0. So what is the concept in this involved is potential of earth. electric potential and not gravitational potential. Electric.
Sir?
Ah.
So when should we use that other charge distribution diagram, sir? In the previous.
Not other charge distribution. If somebody has, find the surface charge density on all surfaces.
Okay.
You should know all things, my year. Not like only like a question asked to calculate answer. Actually, this word electrostatic induction occurs. Looking at this diagram, we should calculate. This will become more time consuming. We are avoiding it. Huh?
Yes, sir.
No, electric potential of Earth is 0. Then what is this? This is a conducting wire. Huh? There's a conducting switch. I'm making things clear. What all we are going to learn now. The application part of this, you can see benefit in 2 chapters. Current density and capacitors. What all you learn, conductors. What all you're going to learn, no, conductor equipotential, electric field should be directed perpendicular, net field inside the conductor due to static charges, 0. All these ideas you are going to help in. The 2 chapters revolve around these small basic ideas. Just core fundamental ideas is what we are going to use in the coming chapters. Okay, now earthing of shells. So electric potential of Earth is 0. We know conductor is an equipotential. Will I agree? Let me give a general first description. So there's a body is there. There's a body. No. There's iron made up of iron. This one. Now what I do is like there's a wire. And it will be connected to Earth. So I have so to make you imagination, I'm bringing all this. This is Earth. We know what is the potential of Earth is in fact 0. The potential of Earth, we take it to be 0. Now that the iron body is there. So it's a conductor, no? Iron is a conductor. Now the Earth is what is the reference for us. It's like a sink, electric sink, you can call it. It's having a 0 potential. So potential of Earth is how much will be 0. Whether you add charge or take out charge, it's like infinite sink, like in thermodynamics, how we had a sink, no? Similarly, what happened in like a electrostatic, this will be like a sink, you can say, like you add any amount of charge to it or you take out any amount of charge, what happened to potential of the Earth will remain 0. Potential of Earth will be 0 when some charge gets added up, because what is the capacity of this will be infinite. Am I right? Okay, there's a conducting wire. Copper wire, I'll write it. No, what is the potential of this? Potential of Earth, I'll write it ground. So what is the potential? So this will be 0. No, there's an iron body. So let's assume that it's having some potential. Then copper is also a conductor, no? So when I join, so this is very important. There's a point A, there's a point G for us. No, there's a copper wire, no? So when I close this, this copper is also a conductor. Then potential conductor is equipotential. So then what this wire will do will make potential of this iron body equal to that of the Earth. The reason for that, this wire is a conductor and conductor is an equipotential surface. Getting the idea? Getting the idea now? So how to make potential of this iron body equal to 0? Just connect a copper wire between that iron body and the Earth. Then potential of that will become 0. Conductor is an equipotential. On closing switch, potential of A will become equal to G. Potential of the ground is how much, or Earth, it is 0. So therefore, potential of the body also will become 0. So when I close this switch, Potential A equal to G, and potential of G is 0. So therefore, what is the potential of A will also become 0. Okay, fine now. So any body, any conducting body, if it is earthed means by using a conducting wire, I'll connect it to the ground. The ground is what we say, no? So it's called like a grounded or earthed. This symbol is used for earthing. Instead of drawing the earth symbol R, no, we just show by this. It is assumed that it is earthed. All of you got the idea? This one? Okay, let's sum that one. So what is the conclusion now? When any conducting body earthed, potential of that will become 0. When a conducting body earthed, its potential becomes 0. Okay, similarly, that earthing is what we are going to do here now. Okay, now he's asking, after earthing, the shell A and B are given charges Q and 3Q. After earthing, I'm asking what will be the charge on each surface. Then what is the potential of the shell which is not earthed? Find the charge on each shell and potential of shell A which is not earthed. Okay, now what is the method? Here, I don't know what happened final charges after earthing. The switch is closed, so conducting wire, you better write. Switch, anything that it be. Okay, now what is the charge here? Let the charge here be Q1. We don't know what are the charges. Then here charge Q2 and final charge Q3. And then what we are going to do is like we are going to take help of. Again, a small procedure is there. Follow that procedure. It will be very easy for you. So this is the inner shell. The outer shell, where is the pink color? Oh. It's in fact thin. All the shells are thin, but what I do is like to make you understand, I'm making tick here, that one. This is R. This is 3R. Now what I do is I'll ask you to assume a Gaussian surface in the material of shell B. Now what are the charges we give? So this will be, this was the charge Q1, Q2, Q3. No, where is there's a shell A, there's a shell B. What will be the net field at point P? Net electric field at point P, because the point P lies inside the conductor. We know Gauss law conditions, conductors. The net field inside the conductor due to static charges must be 0. So therefore this EP must be 0. If EP is 0, then flux should be 0. Net flux 0, net charge enclosed is 0. So therefore Q1 plus Q2 equals 0. This is the equation 1. Everywhere you can use, not only this problem, everywhere. No, a shell which is not earthed, the charge of the shell should be conserved. No, we'll apply conservation of charge principle. Which shell is not earthed? Shell B is not earthed, so charge of shell B should be conserved. So what is the next idea? The charge of shell B is conserved because there's a reason it is not earthed. What was the charge of shell B? 3Q. So therefore 3Q should be equal to Q2 plus Q3. Equation 2, I got it. How many unknowns are there? Q1, Q2 and Q3. 3 unknowns are there. I have 2 equations. I need one more equation. So a shell which is earthed, what should be the potential of it? Which is, oh, so wait. Shell B is earthed, no? Charge of shell A is conserved, sorry. Charge of shell A is conserved. What was the charge given to shell A? Q. So therefore, From 1 to what we can write it? Q2 equal to minus Q. So what all the charges we got it? Please notice shell B is earthed, no? Shell A is not earthed. So charge of a shell which is not a charge of shell A is conserved because not earthed. What was the earlier charge given? Q. No, the charge will remain same as it is, Q1. Then from this equation 192, Q2 equal to minus Q. So what is the charge here? Q minus Q. We have to calculate this charge. Now, a shell which is earthed, what should be the potential? When a conducting body is earthed, its potential becomes 0. So shall I write expression for potential B 0? Then I'll write equation potential B should be equal to 0. Why it should be 0? Because shell B is earthed. Okay, let's write equation. Okay, this thing. No? What is the potential of shell B? Can we write it? Again, the superposition principle. First, KQ1 3R, KQ2 3R, KQ3 3R. Just now you all learned it. So we know Q1 plus Q2 0. So solving this, Q3 will become 0. What is the potential of shell B? KQ1 3R, KQ2 3R, KQ3 3R. Q1 plus Q2 is in fact 0. So finally we'll get Q3 0. Means there won't be final charge here. Now what will be the system? How do it will appear? The whole system, how do it will appear again? What are the final charges? This will be Q minus Q. This will be 0. This will be your final system. Okay, now looking at this, I am asking you to write the potential of shell A. A shell which is not earthed, its potential should be determined. I think, okay, you are able to see. Yeah. How to write potential of shell A? K Q by R plus K minus Q by 3R. 2KQ by 3R.
Sir,
Mama.
but potential at B will be 0 now, sir.
Yeah, okay, I wrote 0, no.
No, sir. So that only potential at A should be only KQ by R now, sir.
Superposition principle, ma, when you're calculating potential at shell A, looking at this diagram, KQ by R minus KQ by 3R. I know potential of shell B is 0, no doubt. But when you're calculating potential is at a given point will be due to charge on all surfaces, whether you earth a shell or you don't earth a shell. Huh? Okay, I think I'm giving complete description of problem, see once. All these are not concept, just method. 1 or 2, 3 problems, if you understand, you can manage very easily. Shall I scroll down?
Sir.
Somebody is asking. Thick shell, I'll come to later on. Let's only focus on thin shell. Let's have a clarity. Tomorrow I'll focus on the thick shell. Because at a time it'll become cocktail. Maximum students will get confused. That's why I'm avoiding the thick shell now. Can you hear me? There's no electric power with mobile data. I'm running the show. I'll try my level best. I don't have any option. Okay, no question. I have water.
Sorry, voice is cracking.
Can you hear me? Shall I continue?
Sir, voice is breaking.
So,
Yes, sir. Voice.
no. Still breaking. No, okay.
No, sir, still correct. No, sir, still breaking.
Still breaking. Other sources. I'm using this mobile data at least. Can you hear me?
No,
Your voice is breaking.
yes, sir, it's cracking.
It's connecting the. I'll do one thing. I'll do the video filters. No, can I continue?
Sir, it's still breaking.
Still breaking. Sir.
No, can you hear me? Almost everything, all unnecessary things I removed it.
Still breaking.
Okay, still breaking. No?
No, sir, we can't.
Oh, what shall we do? Even
Still breaking.
your voice also cracking is there. First, pause recording. Recording. Yeah. Two concentric shells. Two concentric shells A and B are given charges Q and 3Q, and then inner shell A is earthed. Inner shell we are going to earthed. Find the charge on each shell and potential of shell B after closing the switch. I think this is a condition. Now what charges will be there? We don't know. Again, what is the method? So charge on the shells, let it be Q1, Q2. Don't do one thing. So this is a Q1, this is a Q1, minus Q1. Don't do like this. Right? Charge on all surfaces, Q1, Q2, Q3. Then from Gauss law, if you draw a Gauss interface, the material of shell B, the net field should be 0. So from there, the very first condition, what do we get? Q1 plus Q2 equal to 0. Is it okay? They're the first primary condition. Then next after this, what we'll write it? Shell charge of a shell which is not earthed. Which shell is not earthed? Shell B is not earthed. So what was the charge given? 3Q should be equal to Q2 plus Q3. From where this charge of a shell B is conserved as it is not earthed. Equation 1, equation 2. Shell which is earthed, potential of that should be 0 as shell A is earthed. Okay, now we'll write potential of shell A. What is the potential of shell A? This should be equal to K Q1 by R, K Q1, K Q2 by 3R, K Q3 by 3R, all set equals 0. Q2 plus Q3 is equal to how much? From the equation 2, so this is equation 3. Solving 1, 2, 3, we'll get the charge on all surfaces. So put 2 in 3. Or further this, Q1 equal to Q2 plus Q3 by equal to 0. So Q2 plus Q3 is how much? 3Q. So therefore Q1 equal to minus Q. If Q1 equal to minus Q, then from 1, Q2 should be equal to plus Q. Okay, Q2 equal to Q, then Q3 should be equal to from 2, Q2 should be equal to 2Q. Okay, these are the final charges. Okay, look at once the procedure. Now shell B which is not earthed. So what is the potential of that? How to calculate that potential? So the formula will be VB is equal to then K Q1 by 3R, K Q2 by 3R, KQ3 by 3R. Substitute all Q1, Q2, Q3. So Q1 plus Q2 should be equal to 0. So Q3 is equal to how much? Oh, this is Q3, no? Okay, I'll make change. This is. So potential of this will become 2KQ by 3R. Okay, are you getting the procedure? A shell which is earthed, potential of that should be 0. A shell which is not earthed, potential of that need not be 0. Then charge of a shell which is not earthed should be conserved. Then applying Gauss law, the net field inside the conductor must be 0. So with the help of that, get the relation between charges. There are, I think, three important points. What is that? What are the things? Net field inside the connector, whether this is earthed or not, irrespective of that one. Q1 plus Q2 must be 0, no? Because net field inside the connector at this, inside the metal of shell B should be 0. It's a conductor. So if I draw a Gaussian surface in the metal of shell B, the net field should be 0 inside the conductor. So therefore Q1 plus Q2 must be 0. This is a universal in any number of shells, which are shall be earthed. Then a shell which is not earthed, charge should be conserved. What was the charge given to shell B? 3Q. How much? Q2 plus Q3. Then shell which is earthed, potential should be 0. Solving that will get the required answer. Okay, I'll proceed to the next. 3 shells will take it. The two earthings I have brought it. And then we'll see what conditions we'll get. Huh? Okay, now read the question. So we have switch S1, S2. First following cases. What is the following case? Switch S1 is closed or shell B is earthed. Carry on. So again, what is the procedure? Shall we go like this? I think now you can see a lot of calculations are there. Just be careful. Q3, Q4, Q5. No. Okay, after getting this, now first again applying drawing the Gaussian surface in the material of shell B, drawing the Gaussian surface in the material of shell B. So we'll get Q1 plus Q2 0. This is basically our primary question. We'll first write the equation. So Q1 plus Q2 is 0. Why Q1 plus Q2 0? By applying Gauss law in the material of shell B. I can't write all the data. Please do assume. So just for your convenience, if I write field strength at point P means it is understood. Okay, this and then similarly, I'll draw a Gaussian surface here in the material of shell C. Then again, what is the net charge it will enclose? Q1, Q2, Q3, and Q4. Agreed? Not understood, I'll draw the diagram. Understood means, okay, I'll directly write the equation. Similarly, I'm asking you to make the shell C a little bit thick, draw their Gaussian surface. So the point P lies now inside the material. So net field here should be 0 inside the conductor. So what is the net field? 0 means net flux should be 0. Net flux means net charge enclosed 0. So Q4 plus Q3 plus Q1 plus Q2 should be 0. So what is the at least equation we can write? Net field in the shell B in the material must be 0. Similarly, Q1 plus Q2 plus Q3 plus Q4 equals 0. Same expression will dump for this also. Net field in the material of shell C must be 0. Okay, already Q1 plus Q2 is 0. So therefore, Q3 plus Q4 will be 0. I think these are things which are going to help us a lot. Put it here now. Let's come for this one. Which shells are not earthed? Shell A and C are not earthed. So charge of a shell not earthed should be conserved. So then what was the charge of shell A? Q. What was the charge of shell A? Q1. So therefore, Q1 should be equal to plus Q. Any reason for that? Charge of shell A is conserved. Similarly, which shell is not earthed? Shell C is not earthed, no? So what was the charge given to shell C? 3Q. So therefore, Q4 plus Q5 should be equal to 3Q. Charge of shell C is conserved. Okay, I think we have so many equations, set of equations are there. This is due to other condition. Okay, no, which shell is earthed? Shell B is earthed, so potential of that should be 0. Okay, let's write expression for potential of shell B. Looking at the which diagram? Looking at this diagram, not here, this one. Looking at this diagram. No, potential of shell B, the equation should be equal to K Q1 by 2R, K Q2 by 2R, K Q3 by 2R, K Q4 by 3R, K Q5 by 3R. This should, everything should become equal to 0. So K by R get cancelled. So Q1 by 2, Q2 by 2, Q4 by 3, Q4 plus Q5. Okay, this will make it one common. Q4 plus Q5 will be 3Q. And Q1 plus Q2 is 0. So with that, I think we'll make these two as common. Q1 plus Q2 is how much? Equal to 0. Q4 plus Q5 is 3Q by 3. So how much? Q3 equal to minus 2Q. Okay, I think that's the first answer what we got it. Okay, once you know Q3, can we find out Q4? Here, look at this. Q4 equal to minus Q3. So we'll get Q3. Then once you know Q3, once you know Q4, then you'll get Q5. Already we know Q1, then we'll get the Q2. I think it's 4, no? Almost everything will end up. So let's write all the things now. Therefore, if you know Q3, Q4 is equal to how much? Plus 2Q. If Q4 is 2Q, Q5 will become Q. Q1 is already Q is there. So Q2 will be minus Q. So what will be the final charges on system? The final charges will be What will be the final charges? We will write down all. Q1 is Q minus Q. Q2 is Q2 is minus Q. Q3 is how much? Minus 2Q. Q4 plus 2Q. Q5 Q. Can we find out potentials after getting these potentials? Potential of shell A. How to calculate potential of shell A? I'll go for the next calculation. So potential of shell A. What all I should do? KQ by 2R, K minus Q by 2R, anybody value? KQ minus QR, and these two will cancel out. So minus KQR, here this will be plus K. Will it be 0? Check once. I'm getting 0. Anybody verify it? Okay, possible. Similarly, potential of shell C, the similar method. KQ by 3R will come. After earthing, this is after earthing. You see, shell B is earthed. Even 3 shells also, the method is same. Any doubt, please clarify. Any doubt if you have, you can clarify it. 0, yeah. It can happen. The way we have chosen charges, no, the distance it can happen. Yeah.
Sir,
Mama, yeah.
sir, in potential at A, is it not KQ by R, sir?
Where I think the first one, no, what I
Yes.
wrote. Oh, two,
Yes,
it
sir.
should be.
It should be.
I think that the answer will change, no. Check now the answer. You check it. KQ by R. What I wrote, KQ by R, KQ minus 2R. Yeah, fine. Yeah, some correction is there. Anybody value no?
KQ by 2R.
KQ by
2R.
2R. So they may ask you potential difference. One shell earthed potential difference. Let it be no problem. The method is same. These are very popular. Can be asked in mains or advanced anywhere. Looks simple, but still they can ask you. If shell C is earthed, I'll scroll down. Switch S2 is closed or shell C is earthed. When next again is putting both the shells are earthed. Okay, again the method is same. Q1 plus Q2 should be 0. The same. So we will begin like this. So I'll put the charges. This will be Q1, Q1, Q2, Q3, Q4, Q5. Shell C is earthed. Then first thing what we can write, Q1 plus Q2 should be equal to Q. What was the charge given? I think I I need this diagram. Then we'll delete it. Copy. Yeah. Okay, we'll keep this diagram in mind. This was the original question. No? Okay, first Q1 plus Q2 is 0. Then Q1 plus Q2 plus Q3 plus Q4 is 0. Since Q1 plus Q2 is 0, therefore this will be there's a 1. These two by Gauss law, by applying Gauss law, these two are. Then again, which shell is earthed? Shell C is earthed. Then charge of a shells are conservation of charge. Okay, these are by Gauss law for your right. By Gauss law. Then by conservation of charge. Just see that ideas are very important. The problem may change by conservation of charge. We shall what we can write? Q1 must be equal to plus Q. Shell A is not earthed. Then shell B is not earthed. So therefore Q2 plus Q3 should be equal to minus 2Q. This is exclusively conservation of charge idea. Then which shell is earthed? No, shell C is earthed. Potential of that should be 0. The reason for that, shell C is earthed. No, as shell C is earthed. So what is VC? So we'll write it. KQ1 by 3R, KQ2 by 3R, KQ3 by 3R. What I think from looking at this one, Q5 will be 0, no? Looking at the data, compare the equations. Oh, yeah. 0, 0, it should be. In hurry, I'm writing. Yeah. Q5 must be 0 by from that one. Q5 will be 0. After getting Q5 0, then come for this one. Let's therefore Q5 is 0. If Q5 is 0, let's come for this one. Q1 equal to Q, so Q2 equal to minus Q1. So Q1 equal to Q, Q2 equal to minus Q. Then Q2 equal to minus Q. So how much will be Q3? Q3 will be minus Q. Q3 minus Q, then Q4 will be plus Q. This will be the final charges. So what is the one conclusion? Whenever the outer shell is earthed, charge on outermost surface will be 0. You see, are you noticing? I think that you compare all the problems. The charge on outermost surface of outer shell will be 0 when that shell is earthed. Shell C is earthed. What will be the charge here? Will be 0. Check in all the cases. But if you earth any other shell, this charge will not be 0. When outermost shell is earthed, the charge on outermost surface must be 0. You can see any number of shells, you take it. If you earth outermost shell, then the charge on outermost surface must be 0. Outermost surface of outer shell must be 0. The charge outermost surface of outer shell must be 0 when outermost shell is earthed. You do get more than one options, questions of these kind. So you do think that it's a concept? No, from numerical. When you solve some 4-5 numericals, and when you make observation of numerical, then you are able to conclude. So very dangerous these things are. So in advance, these are the types of questions you get it. So in physics, conceptual question is not like any other subject where you have to just think. Again, the conceptual questions are again, they are numericals only. We must take some example, then we can pick up a suitable options. Most of the physics theoretical questions are not just theory. They're again revolve around numericals only. If both the shells are earthed, tell me what conditions will come. Again, the first two conditions are valid. No, that there is a no doubt in these two. We'll just continue again here. The first thing. Then a charge of a shell, which shell is conserved? Only that one. So Q1 is equal to how much? Charge of shell is conserved as it is not earthed. So Q1 equal to Q, so Q2 equal to minus Q. That's all. What about the shell B and C? They're earthed. So potential of shell B 0, potential of shell C also 0. Solve it, you'll get the required answer. I can earth shell A and C also. Potential of them must be equal and equal to 0. So write equation and solve it. And in fact, they're earthed, no, it should be equal to 0. Can you work out? I'll go for the next idea. One more. No, instead of earthing, no, let me join by a wire. There's nothing but a Van de Graaff generator idea. What are VA and VB values for case 2? What are VA, VB? You have to work out, calculate potential of A and B as usual. Calculate. How to calculate potential? Work out. Somebody has to calculate. Okay, no, the next one is I'm going to join a wire. VA KQ by 3R, VB KQ by 6R. I'll write down, somebody please check it. VA KQ by 3R. After earthing this. I had to work out, so I don't have anything. Okay, others you verify the values potential of shell and B when shell C the earthed, no. So these are the values proposed. Meghana, are they correct?
Yes, sir, I'm getting that, sir.
Okay, fine, Meghana. Others you can verify later on. Yeah. Now this one, the next concept. I am going to join a wire from inner shell to outer shell. This is called like a principle of Van de Graaff generator. It's an experiment. That experimental setup is there. You just type in YouTube, no, Van de Graaff generator. You get one video, watch that one. Because again, that it will take almost 1.5 hours for me to explain that experiment, all that one. It's a self-explanatory and not part of syllabus also. This is called like a principle of Van de Graaff generator is what I'm discussing. Okay, now what do you expect? The charges given are Q and 6Q. Okay, just general question. Which charge is more? 6Q charges more than Q, no? Then when I close switch, what do you expect? Some charge will flow from outer to inner shell, so that how long the charge will flow? Go back to electrostatics. The charge will move from higher to lower potential. Am I right? Positive charge will move from higher to lower potential. Okay, similarly here also same thing. How long the flow of charge will occur? Till potential of shells become equal. E equal to dou V by dou X, the idea what we have generated. If you release a charge, positive charge in an electric field, it will move from higher to lower potential. Same thing here. Now charge will flow from outer to inner shell or inner to outer shell. We'll determine the potential difference between them. We'll calculate potential difference. We'll see. Then will some Q charge from outer shell will flow to the inner shell, or some Q charge from inner shell, some charge from inner to outer shell will flow. We don't know anything. Let's work out. So after closing the switch, after just closing the switch, what charges are there? After closing the switch, it's a conducting switch, no? This particular switch is what happened made up of iron. These are conducting shells again. Copper, thin copper shells. Two thin copper concentric shells. Huh? Let's get into this one. What actually happened? So I'll assume that some Q charge will flow from inner shell to outer shell. And what was the charge here? I'll give red color. Agree this, I think good justification. Some Q charge has flown from here, from inner to outer shell. No, as this iron, why no? So we know what is iron? It's a conductor. So when you join two conductors by an iron wire, what will be the potential of those two conductors? Should be same, because iron is a conductor and conductor must be equipotential. So what this wire will do, will make potential of shell A equal to that of B. Okay, I'm interested like how much of charge, no? Like how much of charge has flown through the wire. That was our primary question. Okay, let's get into potential now. Potential of A equal to potential of B. I'll do here. Now, why potential of shell A equal to B? Because they're connected by a conducting wire. And conductor is an equipotential. Okay, what is potential of shell A? Looking at the diagram, K R plus K 6Q plus Q 3R is equal to K Q minus Q 3R. Okay, fine. Potential of shell A and B. Similarly, like just now we learned, no? Potential of shell A. Charge on shell A by radius R. Then this particular point will lie inside the shell B. So therefore 6KQ plus Q by 3R. If I stand here, first only due to potential of shell A, KQ minus Q by 3R, then due to shell charge on shell B, this much here. Okay, these two will cancel out. So I'll end up with the equation of like this. When this will be valid? This will be correct only when mathematically when Q equal to Q. If small q equal to capital Q only, then on this equation become valid, no? So then what does it mean finally? The whole charge on the shell A will flow to the outer shell. Looks strange, but this is what happens. So what is the final? Finally, what happened? We'll get here 7Q charge. And here 0, no charge. Agree this? So what was the what we expected? 6q. So some charge from outer shell will flow. No, the charge from inner shell is flowing. Okay, next what I do is instead of this q, no, let me bring minus q. then also that minus q will flow to the outer shell. So irrespective of potential greater than VA greater than VB, VA less than VB, the charge will flow from inner to outer shell only. Now I'll ask you one of the best question. Which will be at higher potential, VA or VB? Who will answer? Looking at here. So now shall we give answer that one? The charge has flown from inner to outer shell. The reason potential of shell A is greater than B, that's why it has flown. That was the reason. Okay, so time being, okay, there's a reason. The charge flows from inner shell A to outer shell B as agreed. I think shall we give reason? Okay, next student, what happened instead of this? Let me keep minus q. What changes will come? Again, you're going to write minus q. Minus q. Then we'll solve it. I agree this. I'll change the data because we have to verify for VA less than VB what conditions will arise. Okay, now the second condition is
Sir, if we take a q minus q, we will get the resultant as a minus q, no sir? The charge transfer would be minus q will get, no sir?
what you are asking.
Sir, if we take you substituted k into capital Q minus small q by r, no sir? If we take instead of small minus q, if we take plus q.
Not like some charge here also depend. There's some charge will leave. What charge will leave, we don't know.
Yes, sir.
I don't know. No. At least can you say about potential now? Which will be at higher potential? So first we'll calculate potential. Potential of A equal to K minus Q by R, K 6Q by 3R. This will be KQ by R. VB equal to how much? K minus Q 3R. Which is at higher potential now. VA less than VB. Before closing switch, this is before closing switch. Similarly, here also you can calculate the first diagram. This is I brought minus Q. All of you, I changed its situation. Charge on shell A is negative now. Earlier the charge on shell A was positive. I changed problem. There's a case 2. What we discussed is case 1. See, all these are conceptual things. Unless through numerical only we can analyze. Not possible. Theoretically, just I can't write sentence. Yeah, I think you have everything in front of you. Make observation. No. VA less than VB, I'm very sure. I'm going to close switch. After closing switch, what will happen? I'll draw a small diagram. I don't have space. R, this is 3R. No, in this case, it will be what will be the final charge? I know some charge left. Minus Q negative signs, no? Yeah. Minus q, this was plus 6q. So what shall we do? Some charge left. Charge left means will become, let's solve again, since they're connected by a wire, no? Iron wire. So what happened to potential of shell A and B must be equal. Let's write the same equation, K see this again, what is the basic necessity condition? So this minus q should be equal to 0. So therefore, what should be the q charge? Should be equal to minus q. So how much of charge has flown? The whole negative charge will flow to the earth. So finally, what will be our diagram? Our diagram will be like this. I have space only this much. I'll end up here. So what is the conclusion we are going to make is the final charge, how much here will be 5q when you join by a wire. So what we thought, like, since VA greater than VB, charge has flown from inner to outer shell. Look at here now. VA greater than BV or VA less than VB, irrespective of that, what all charge present on inner shell will flow to the outer shell. This is what I'm going to use to produce a charge on a shell. How to produce charge on a shell? It's not that easier. Not like some charge will present in some bottle. I'll take spoon, I'll sprinkle it. Not there. We have an like a Van de Graaff generator. It's an experiment. Through that experimental setup only, I can produce a charge on a shell. For namesake, I'm saying charges are given to shell. To give that, I need minimum half an hour. To produce a charge on a shell, no, we need some half an hour time. It's experimental setup. So I think this will be much easier, no? So I need not to bother. So like, what will be that? What is the charge on a shell that will be transferred? So I want to like a charge in this particular shell. So I'll give some charge to shell A. I'll join a wire. The whole charge will flow. I think very fine, no? What charge you give to shell A, that will go to the outer shell when you close switch. I need not to bother any mathematics here. Whether I'm giving positive charge, whether I'm giving negative charge, nothing. What all charges there will flow to outer shell. Irrespective of what charge is present here. So you bring 100Q. Sir, 100Q. So 100Q. So more charge, sir, some charge, let it flow like this. No. Even if the 1 lakh coulombs, here 1 coulomb, the 1 coulomb will flow from inner to outer shell. Whether inner charge on inner shell is positive or negative, whether it is greater than or less than. If there's a greater, there's lesser, still it will flow. There's a lower value, there's a higher value, still it will flow. So what is the condition now? When you join two concentric tin conducting shells by a wire, conducting wire, what all charge present on shell A will flow to the outer shell. The charge Q flows from inner shell to outer shell B as VA less than VB. Yes. So is it a correct statement? Not must, may. Even so I can write sentence, no? The charge Q flows from inner shell A to outer shell B as VA less than VB. Yes. So there is nothing called like this is something like a only when VA greater than VB charge flows. VA less than VB or VA less than V. So what shall I write? The charge, generalize, I'll make it VA less than VB or VA. I think this statement will be very generalized one. The charge flows from inner shell A to outer shell B as VA greater than or VA less than VB when joined by a wire. Without joining wire, charge cannot jump. Yeah. This will become generalized statement. So even the Van de Graaff, no, he was surprised when he got this one. He was surprised. Then he could not believe. Then he did experiment. Then finally concluded, oh yeah, there's a very thing. So I think based on this now, it has become very easy for him to generate a charge now. I need not to bother anything. No, what all charge of shell A will go to outer shell, irrespective of VA greater than VB, VA less than VB, whether this is negative, this is a positive, this is higher, this is lower. Irrespective of any conditions, charge will always flow from IA to from inner shell to outer shell. Is it a positive charge or negative charge, irrespective of that also. This is called like a principle of Van de Graaff generator. One more last, and we'll go for counseling up because many doubts will be there for you to clarify. Now there's a thick copper shell. A point charge Q is kept at the center of the copper shell. We have to calculate potential at the center of this one. A point charge thick neutral, not at center, is kept at a distance, say, from center of thick neutral copper shell. Okay, now what will happen? Okay, already yesterday we had some cavity idea. Okay, the same thing is what I'm going to consider it. Okay, this is the thing. So what it does, it will induce charge. It will induce more charge here, no? And the charge on outer shell should be uniform. Yes, no, look at this one. How much of net charge? What shall I net charge? It should be minus Q. The net charge on outer surface should be plus Q. Any reason? Why not minus Q here plus 2Q? It's a neutral, no? And electrostatic induction, net charge should be conserved. So minus Q plus Q will be 0, that one. So now also it's electrically neutral. Then what are the questions that are asked? It's asking to find out the potential at center. Find potential at center O of shell. This will be a very difficult question. How do we get potential at center as it is? What is the potential? We should take superposition. Potential first due to point charge. Okay, there's a point charge. Somebody is asking, sir, where is the point charge? Fine. There's a point charge. Okay, now when it comes potential, what we do? Superposition due to all the potential, like a sum of potential due to individual charges, system, better you call, potential due to this. We'll write all one by one. V naught equal to first KQ by A. At what distance the point charge is there at a distance A? So KQ by A. Next again, this charge is non-uniformly distributed. Can we write potential? Yes, we can write. Because like you take any point on this inner surface, it will be at a distance R only. So what is the net charge on inner surface? Minus Q. So this will become K minus Q by A. Q by, sorry, this is R. let me have it. Then similarly, like next again, assume that all this point charge and this minus q is not there. Then where the point O will lie inside the shell, then what is the potential on the surface? There should be the everywhere potential inside. So then this will become kq by 3r. So kq by a, this will be minus 2 kq by 3r. Only at center, this is potential. At center, okay. Now, what about the electric lines of force? How the lines of force will be? What about the charge on outer surface will be uniform? Inside, the lines of force will not be uniform. So like inside, what happened? It will be like you can show it. So whereas here, this is similar to like a charged conducting sphere we have. So I won't know the potential at point P or the field strength at point P. Field strength at point P is similar to that of there's a charged sphere, no? So kq by r square. What is the field strength at point P? Somewhere here I'll ask you. So what is the field strength? Is just given by kq by r square. Because this field is uniform. It is produced similar to that of uniformly charged conducting sphere. So what is the strict condition? This is valid only when r is greater than 3r. Okay, look at once. These are the now slowly will take the, see, we don't have very lengthy questions, all different situations will come. Any doubt related to this, you can clarify. I'll wind up some, many doubts will be there. Okay, some half an hour, at least 40 minutes time is there. We'll go for doubt. Huh? I'll wind up the class. Okay, try to work out different types of numericals available. Huh? Okay, we'll meet in the next class. Now the charge is uniformly distributed, no? Okay, I'll end up once. Okay, thank all of you. Take care. Bye. See you.